Ready to start. This is the attendance sheet, the one that you guys missed last time. So let's pass the attendance sheet through the room and make sure it gets to everybody. Like before, we write a big bullet on the left side. Okay, this is not part of your grade, just I want to keep track of who's here and who's not. We go first up, then down, then up, back to the very end. So today, we are going to recap very quickly the binary representation, which I already kind of write it here. That's all stuff that you have seen in the past 2 weeks. And then we're going to start talking about logic gates, circuits, and Boolean algebra, which is kind of a binary world too. It's true or false in here. It's current passes through or it doesn't passes through. And that's how logic board and circuit for silicon boards are built. That's kind of a very, very basic block of them. Eventually, in this line of thinking, you get to how to build a CPU, for example. Although CPUs are extremely complicated. Okay? So a quick recap of binary, like really quick. I show you guys this picture. On 8 bits, my range is from -28 in a signed world to 127. And this is the representation. This is the most negative, +1, +2, up to -1. That would be -127, -128 plus 127. This is -1. If I add one more 1, I get 0, 0, 0, 0. Carry bits out of the 8 pack gets ignored. So even if I add 1 here, I would get the carry bit in 9-bit. I don't care about that because I only have 8 bits. And if I go down all the way to the most positive, that's 127, which is this value right here. Right? And we talked about, this is a signed version. In an unsigned version, we have the same representations, but maybe they mean slightly different things. The positive range will mean the same. In an unsigned world, 1 here will still be 0, 0, 0, 0, 0, 0, 0, 1. But these numbers are not negative anymore. In an unsigned version, we just put here unsigned. What would this number be here in an unsigned? This is not -1 anymore if it's unsigned. In a signed world, this is -1. In an unsigned world, what is this?
255.
255, right? And what is this in an unsigned world? How much is it?
128.
128. So the bits are still 8 bits, 256 total possibilities. If it's signed, it's from here to there. If it's unsigned, then the first bit count as well. And then I give you guys 3 ways to think about this. This is the rule from the book, the one with you write the positive representation, flip the bits, add 1. Right? This is natural way to think about it, write the positive representation. You know if you add the negative number, you should get 0, 0, 0, 0, right? So you figure out what you need to add to get 0, 0, 0, 0. And if that works out, that's the value you need. And I give you guys another one, a recitations, which is saying, take all these bits in a positive way. Only if this bit is 1 here, take it in a negative way. So this bit, when it's 0, counts as 0. That's the regular binary representation. But when it's 1, instead of corresponding to 2 at 7, it corresponds to -2 to the 7. So I showed you guys this recitation that if I take these bits, like regular bits, and I make this one -2 to the 7, I get the 2 complement binary representation. So now, as a 4th way to think about it, you don't really need 4 ways, but sometimes people do it this way, so it's a good mental exercise. I'm going to put these representations, but I'm only going to use 4 bits here because I can't make a wheel that big. I'm going to put them in a spiral. So I'm going to say, here's 0. Let me get it right. Here's 0, and then of course, this is a +1. Everywhere you go that way is +1. So this is 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 1, and this is 0, 1, 0, 0. And then let's here 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. This one here is 1, 0, 0, 0. And now if I keep going, this is 1, 0, 0, 1. Just keep adding 1 to it in a binary world. 1, 0, 1, 0. 1, 0, 1, 1. 1, 1, 0, 0. 1, 1, 0, 1. 1, 1, 1, 0. 1, 1, 1, 1. These are all the possibilities on 4 bits, correct? How many of them are there? If I have 4 bits, how many possible ways to write bits I have on them?
16.
16, because each bit gives me 2 possibilities, 2 times 2 times 2 times 2. This is all the possible strings of 4 bits. So in a signed version, so I'm going to say this is signed here. This of course is 0, this is 1, this is 2, this is 3, this is 4, 5, 6, 7. What is this?
-8.
In the signed version.
Negative.
Do I have an 8?
No.
In the signed 4 bits, I do not have an 8. This is -8. Remember? In 4 bits, this would be the most negative value. The other way, it's subtracting 1. So who is this?
-1.
Negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7. Hands up, who's with me? Very good. Okay, so that's kind of, if you want to think, that's kind of the positive that way. Actually, let's write it down inside the wheel here. Positive, and if I go that way, it's negative. How about in an unsigned world? That's going to be outside here. If I do unsigned, 0 stays 0. I don't have to rewrite that. 1, 2, 3, 4, 5, 6, 7. What about this value?
8.
This becomes an 8. Let's write it here. How about this value?
9. 10. 11.
12, right?
13.
13, 14, 15. That should correspond to my range in an unsigned world. The biggest number should be 15, because I use all 4 bits for content. So now you can see how this spiral wheel goes. 14 corresponds to -2. They have the same representation. And there is a reason for that. Their difference is 16. How about here? 10 put -6, right? I can actually keep going. If I am to write 16, 16 will go here, right? How about 17? Will go here. 17 will have the same representation as 1. Of course, that is incorrect because I'm losing, I need a 5th bit for 17, which I don't have. Here be 18, here be 19, here be 20, 21. What do we notice? The difference between these values?
16.
Always 16. How about here? 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Again, I get 16, right? Difference. 0. The difference 16 gives me 16. Another difference 16 gives me 32. And this next value here will be 33. Again, at 16 difference. 1, 17, and 33 is an arithmetic progression of difference unit 16, right? So how about the other way, negative? This is -8, right? What about if I go minus on minus side, backwards in the wheel? What's the next negative number? -9. Does it make sense to fit in here?
Yeah.
The -9 to 7, what's the difference? 7 to 23, 16. So here would be minus 10, minus 11, minus 12, minus 13, minus 14, minus 15, and if I go one more, in here will be minus 16. So minus 16, 0, 16, 32. What would be the next number if I go one more time against the wheel?
48.
48. How about the other way if I go one more time against the wheel?
32.
Minus 32. All these things have the same last 4 bits, which are, all these numbers will have the same last 4 bits, which are 0, 0, 0, 0. How about the number 50? Where would 50 be on this wheel? 50 would be here. So after 18, I get 34 plus 16. And the next one will be 50 plus another 16. Right? Because the last 4 bits of 50 are 0, 0, 0, are 0, 0, 1, 0. Okay? We're going to see this wheel again when we do modulo arithmetic starting next week. But in a different kind of setting. But do you need this wheel? Not necessarily. Some people find it easier to think this way. And that's okay. Some people find it easier to think this way, or this way, or this way. Some people understand all 4 ways. Some people understand only 2 of them, or only 3 of them. The only thing that matters is getting the answer right. Okay? So I'm not asking you to learn all 4. I'm telling you, pick the one that makes the most sense to you and gives you the most confidence. And don't be worried about the timing if it's a little slow. Of course, if you have to write this wheel and figure out things on this wheel, will take you more time. Still preferable than getting it wrong. Okay? So whichever way makes the most sense to you, use that way to figure out binary representation. All right. So that's our plan for today. But before we move on, so I already recapped binary representation. That's all I have to say about this. Before we move on, I hope you guys have a good night's sleep, right? And a cup of coffee. Because before we move on, we're gonna do something that's master student level. Exciting, extra. I should say very clearly that this is that kind of stuff that if you don't want to hear it, won't affect your grade. You asked for it because you are in the honor section. You didn't have to be in the honor section. So there you go. And then after, move to the PhD. Of course, we can't do those things in detail. But that's the whole point of the honor section, to be challenging, to push you forward. Won't affect your grade. So you can go on Facebook if you don't want to hear this. It's totally fine. So the master level exercise that I have here, it's something that we're going to get to towards the end of the term in a formal setting. So for now, it's a very informal setting. It's just a story. And I'm going to call it Radix sort. That is sorting by digits. I assume most people have seen basic sorting. How many people here have seen or heard of bubble sort? What is bubble sort, really quick, informally?
I've only really heard of it. I can't.
Bubble sort, anybody, informally. And if they not align properly, I keep swapping, right? Bubble. Every time you get a bunch of numbers, every time they don't align in the way you want, you swap them. And you keep swapping them until they align, say, in increasing order, right? How many people have heard of that? Bubble sort, okay? There's another one that's interesting. It's called insertion sort. Also very easy. That says keep only the numbers you have sorted. Every time a new number comes in, do what?
Put it in order.
Put it in the right spot. So if I have already 7, 10, and 20, and the number 9 comes, I put it from the very beginning in the sorted order between 7 and 10. Right? And my point about these sorting methods, again, informally, we're going to talk about them at the very end of the term, is that the complexity, the running time of these algorithms depends very dramatically on how many numbers you have. In fact, they depend quadratically. Insertion sort and bubble sort. If I have 10 numbers, roughly quadratic means they're going to do how many operations? 100. If I have 1,000 numbers, they're going to do roughly a million quadratic, right? So Radix sort solves this tricky part. Now we're not going to see why today. We're going to see why at the end of the term. But I want to show you the method because it's not that hard to follow. So here's a bunch of numbers I have here. I should say, for people who are non-computer scientists, they call it Excel sort. People used to spreadsheets all day long. That's what Excel does when you sort things. So what we're going to do here is going to sort those numbers by the last digit. So we're going to look at the last digit, ignore the rest. And we say, what's the last digit? 977, 963. This is base 10. So we're not worried about what the digits are. If I am to sort them, here's what I think I'm going to get. 720, 355. Again, I'm only caring about the last digit here. 436, 457, 657, 329, and 839. So what did I do? I have now the last digit in sorted order. Right? That's when you sort a big table in Excel by a column. You say pick a column, sort the entire table by that column. Now the numbers are not necessarily sorted, but the last digit looks sorted. Who's following me? Good. What I'm going to do next, so this is sort by unit digit. Right? Then I'm going to do next sort by 10th digit. That is the other digit. But there's a little trick. While now I'm sorting by the second digit, so I'm looking at 2, 5, 3, 5, 5, 2, 3, right? If there is the same digit as in 5 versus 5, see here, this 5 and this 5, they're the same digit. So as far as sorting goes, I could put them in any order, right? Sorting means if something smaller has to go first, bigger has to go last. But if they equal, I can put them in any order, right? Well, the trick here is when I'm going to sort by this second digit, if they're equal, as in this 5 versus this 5, I'm going to keep the previous order. So if they're not equal, as in, for example, these 2 is smaller than the 5. So these 2 will definitely go before the 5s. That's the sorting. But when they're equal, and I have quite a few 5s here, right? 5, 5, 5. Those 3 5s should remain in the same order because the sorting doesn't need to change them. Right? So if I do that, what do I get? 720. What would be next? Again, I'm sorting by the middle digit.
329.
329. What's next?
436.
436. Next?
839.
839. Next?
355.
Now I'm going to those 5s, and because I don't have to sort them, they're all the same, I'm going to keep the order. So the 355 will go here, the 457 will go here, right? And the 657 will go here. So again, it's regular sort except a trick. When we don't have to sort, we keep the previous order, which is actually very useful in practice. You don't want to bubble sort things or change things unless you have to. And then finally, what's my last step? Sort by the last digit, the sort by 100 digits. So if I do that, what do I get? 329, 355. Now this 355 went up because the 3 has to go before the 4s. The rule with keep them previous order only applies when I don't have to sort them. So what's next?
436.
436. Next. 457. Next. Next. And 839. And what do we observe now? Numbers are fully sorted. Okay? There's an intuitive, extremely easy explanation for that. This sorts by the hundreds, so if the hundreds are different, they are in the right position. If the hundreds are the same, it keeps the order of the tens. If the hundreds and tens are the same, it keeps the order of the units. That's why the numbers are sorted. Now this method is better than bubble sort and insertion sort, because each one of these sorts can happen in linear time, aka fast, not in quadratic time. So you could say each one of these sorts is linear time and operations. Say I have 100 numbers. This would be 100 operations. This would be 100 operations, 100 operations. And how many times do I have to do this? 3 times in here. Why? Because I have 3 digits. Maybe I have 5 digits, I'll have to do it 5 times. Maybe I have 20 digits, I have to do it 20 times. But still, this number of digits times 100 numbers, it's much smaller than being quadratic, which is bubble sort. Bubble sort for 100 numbers. So let's write that down. Bubble sort for n equal 100 will be approximately 100 square operations. Again, we'll get to this at the end of the course. It's not a hard thing. This Radix sort for the same number of numbers, 100 numbers, will be 100, which is every sort for a digit, times the number of digits. Which again, at the end of the course, we're going to figure out how many digits are there. But I think it's easy to see that this is fewer operations than 100 squared, because there won't be 100 digits in these numbers. Right? If I have 100 numbers, usually they have less than 100 digits. Faster, yes?
When you do this binary, it's faster than bubble sort, because if you do it in decimal, you still have to sort the integers.
Right, there's some technicalities engineering that I can't go through right now. I'll address that in a second when I connect my computer, because I have an exercise for you extra, which is to do this in binary, but I want to visualize it, so you have to print out some cards.
Does that mean for very small lists that bubble sort would still be more efficient?
It could be, yes. In fact, there's many sorting methods. We only said bubble sort, insertion sort, Radix sort, but if you look at Wikipedia at sorting algorithms, there's a list of 100 things. So, for example, there's one called quicksort, which is the one that's used in practice all the time, which is not necessarily as good as Radix sort, but for small lists, it's always very fast. Yes?
How does this compare to like selection sort, where you like compare all the numbers?
Selection sort is n squared, 100 squared. The one that's guaranteed to be good is merge sort, and on expected, on average, very good and practical quicksort. We're going to talk about those things again at the end of term. I just thought this fits in because we talk so much about those digits, and I have an exercise in binary for you. And I thought this is a cool way for you guys to talk to the non-math, non-CS, your friends, and tell them every time you sort something in Excel, an entire table by a row, and then you sort it again by another column and by another column, you're doing Radix sort. This was invented by IBM for library cards. Back then, there were no transistors. See? We can do graduate level stuff. Okay? Let's do another before we move on. That's another thing. Implicitly, we are assuming what the regular section did in 2 hours, we're going to do in 45 minutes. That is this time. Okay? That's how we get extra time to do graduate level stuff. So somebody gave me this idea, hands up, him, which asked me about an algorithm which I heard of but I was not familiar with. And then when I looked at it, I thought it's quite a cool thing that I'm going to give you a little intro, brief intro, 10 minutes in class, and then some materials for people interested to look at, and then we can talk about it in detail at office hours. So here is that problem. The algorithm is called fast inverse square root. That is for floating numbers. Those are 32-bit rationals. So we're not talking about integers. We're talking about things that have the decimal dot in them, and they write on 32 bits. There are two kinds of float numbers, rational numbers, on 32 bits or on 64 bits. One is called floats, and the other one is called, on 64 bits is what? Double. Sorry. But this is particularly about floats. Now the problem is compute y, which is the square root of x. Now x and y are real numbers here, or rational numbers. They're not integers. This is a relevant problem, especially for graphics. In fact, the algorithm has been developed by people who work on games. If you play Quake 3 Arena, you're probably too young for that. That was like 17, 18 years ago. That was a revelation in terms of graphics. It was so much better and faster than other things. It did many things. One of them was doing this very fast. This is necessary because in graphics, we have to deal with the length of the polygon sides. The length in Euclidean distance, it's called norm. It's like the square root of components added up. And we have to take the square root of the norm to figure out the length of the vector for projections. When you look at a 3D environment, there's a lot of polygons being projected. And this is an operation that's called millions of times. So doing it faster helps a big deal. Now, that was then. Since then, both CPUs and GPUs evolved a lot. They have entire new sets of instructions. The main reason for this being a problem was that this operation, if you remember from high school how you take square root, it involves a lot of divisions. Repeated division, 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 division. Division for float numbers was a very expensive operation, almost like logarithm. Logarithm still is a very expensive operation. If you run a for loop in your computer, taking 1,000,000 logarithms will be much slower than taking, say, 1,000,000 additions. Logarithm is still an expensive operation. Division is not anymore expensive. Modern CPUs, SSC3 set of instructions, can do division fast enough that this algorithm is not necessary anymore. I can just call the square root and then do the division, and I'm done. And it's not faster to do it this way. But 17, 18 years ago, when Quake 3 Arena came along, this was a big problem. Division was not that fast. So how do they solve this problem? There's two steps. Step one is this is y. How many bits are here? This is 32 bits. And this is x. I'm going to split them into 1, 8, and how many are left if there's 32 total? 23, right? 1, 8, 20. These are the representation of these numbers. This is x. This is 32-bit y and 32-bit x. And the purpose, of course, if somebody gives me x, I need to figure out y. That is the task in here, to compute this y. So step one is to think of what's called integer of y and integer of x. Now what this means is I don't change the bits. These are the same 32 bits that represent a number. The number might be, for example, x could be 51.753012. Example. The whole point of a binary representation is to write this number somehow with 32 bits, right? And there is a formula for how to do that. It's much more complicated than with integers. Everything we've done in the past 2 weeks was only for integer numbers. You take a float number, that gets complicated. But we don't have to worry about that. The point is, whatever the mechanism, there are 32 bits that indicate this value. And y similarly, which is this exact quantity, will be written on 32 bits. What integer of y and integer of x mean is take those 32 bits and read them as an integer. So the bits in here, I don't know, it's not this value, but it's a different value. It might be 0, 1, 1, 1, 0, 0, 1, 0, 1. I have too many maybe, because I only need 8. Right? And then 0, 0, 1, 0, 1, 1, 0, something. This is not, by the way, I'm just making it up. It's not 51.75301. Just to be clear, it's not that one. But there's some 32 bits, right? That represent a float number. What integer of that means says ignore the float number. Just read the 32 bits unsigned. Get an integer out of them. That we know how to do, right? Because we just studied that for 2 weeks. Take this number. It might be a big number. It might be a gigantic number. Nevertheless, an integer on 32 bits. So I'm going to think of these representations not as representation of float numbers, but simply as representation of integer numbers. Step number 2 is a gross approximation. Instead of saying y has to be 1 over the square root of x, that's what I need, I'm going to say approximate with the following formula. The integer form of y, that is reading those bits as an integer, is approximately minus half of integer of x. That is reading the bits of x as an integer value, plus some magic constant. Some value that's fixed, I'm going to compute it later. Yes?
So we read it as unsigned?
Yes. I don't think that's critical because this is for positive numbers. Those lengths of the vectors are always positive, and this is always positive. So the first bit will be 0 all the time. Okay? So this is an approximation that relies on some mathematics that said the integer value, not the y. Y is the floating value, but the integer value that you read by reading 32 bits could be approximated by roughly a constant number, which somebody computed, minus half of integer x. So if this is like 32 million, they're going to say as a gross approximation for y, I take this constant minus half of 32 million, 60 million, and that's my guess at what y is.
How did you find this formula?
I'm getting there. Okay? I'm going to get there in a second. Step number 3. This gives me some sort of, if you like, gross approximation or initial approximation. People call it Y0 sometimes. They say, that's my first guess at things. And now there is numerical optimization. That says if you have a function, or it says just say g, g of y is 1 minus y squared minus x. X in here is a constant because the function only depends on y. And you have a guess of, say, y0. We want here the root. We want the value gy to be 0. So we want, what's the y that gives me 0 here? That's called a root, right? So we want to solve the equation. X is given to me. We want to solve the equation 1 over y squared minus x equals 0. But we already have a guess that's very important. This is the same problem as in the beginning, right? This equation here is the same as this equation here, right? How many people can see that? Hands up. That this in here is the exact solution of this equation. The only difference between the original problem and this is what? What's new in here that I didn't have there?
Guess for y.
I have already a guess for that root. So I have already a guess that a good guess would be y0. So the numerical optimization says Now find a better guess. So there's a formula that says a better guess is take that y0 and say 3/2 of the original guess minus 1/2 of x times, I think it's y0 cube or something like that. Okay. So what are the steps here? The first step is creativity. Thinking of these 32 bits not as float numbers, but as integers. Second step is to say, I'm going to find a gross approximation, which is not a solution, but it's close. The point is to do it very fast, because we can solve this exact. It's just going to take a lot of division, so it's going to be slow. The third step is, once you have a guess of the solution, can I get a better guess with a numerical optimization function? Okay? Now, there's a lot of details in here, right? A lot of details that we have to go through.
In the formula to find a better guess, how do you know what x is?
X is fixed, is the value you got from the beginning. This is the original input. This is that x.
Right.
Good question. I actually, my PhD student wrote this note for me, and the first time I read it, I was like, who's x? Oh, wait a minute, x is the original input. I had the same exact question. But one PhD student, very good at math, he figured this out. It was not me, he did it. He's a machine learning PhD student. So, a recap. Do we understand step one? We should be able to understand step one. Even if we don't know how the numbers are represented, float numbers, whatever representation is, we can read it as an integer. We take those 32 bits and we make an integer out of them, just like we studied in the past 2 weeks. Now, these steps require mathematics. This in here, turns out it's easy. I'm going to show you a plot that's going to say how good this approximation is. And it's just a good approximation, because I show you 2 lines on the plot, they look the same. So that means a good approximation. This in here requires calculus and derivatives, but it's not that bad. Isaac Newton figured this out 400 years ago. This is called the Newton method. And I'm going to show you that also visually. Now, to get the exact details, you're going to have to go home and study a lot of math. But the intuition of how it works is not too bad. So, let me try to do that. You can pull this off. Again, this is an informal conversation, totally extra. In fact, I'm not sure the dean will agree. If you say, you know what Virgil did in class today? Newton's method, the dean might be, buddy, what the heck? This is not right. So, I mean, that's what I'm saying. Don't get scared if you don't get it, because many people don't get it, right? Like, I bet many faculties don't get it if you show them. So it's PhD level material. It's no problem not to get it. But let's see if we can get a little bit of intuition of this stuff, okay? So here it is. What I want to show you first is this PDF that my student wrote, somewhere here. Should be on the website too, on the public website. So here's how numbers are represented, float numbers in 32 bits. That doesn't matter for the main idea of the algorithm. It doesn't matter how they're represented, but the representation is sign, first bit. Then there is a bit index, that's a fraction part. That's the 0.517532 as an integer is written on those 23 bits. So the maximum number of quantity without the dot, the maximum integer is like 2 to the 23 or something like that. That's just a binary representation. And that thing in there is an exponent, which the biggest is 127 and the smallest is minus 128. So how it works, intuitively, I get an integer value like this, and then the exponent tells me where the dot is, right? If the exponent is 0, I get something like 0 point that. If the exponent is -1, I get 0.05. If there's -2, 0.005. But it stays the same decimals after that. And if the exponent is positive, like in 3, what do I get? The dot goes where if the exponent is 3? After 51, right? It's 51 point something. If the exponent is 4, I get what? 517.532. If the exponent is 5, I get 5,175 times something, right? So there is an integer which is on 23 bits. There is an exponent which tells me where the dot is. And keep in mind that this is up to 127. So what happens when the exponent is really 127? Where the dot goes?
After that.
The dot goes here, right? There will be a huge number in here. And if the exponent is -127, where the dot goes? All the way here. So that's 0.0000005, right? Very small number. Now, the range is good, it's very big, but not a lot of numbers cannot be represented. It's not that granular. That's why we need sometimes 64 bits to represent more numbers. The reason for 64 bits is not to give us a bigger range, necessarily. It's to give us more precision, more decimals in there. So that's how it's represented. And then, what is step 2? What this gross approximation relies to? That relies on approximation that has to do with logarithms, which tells you that if you take the log of those quantities, not the integers, the log of them, they look very, very similar. See the blue line and the red line? That tells you that for the entire range from 0 to 1, the red and blue are very close to each other, right? That's what it makes, instead of this, the red and blue, one corresponds to this approximation, and the other corresponds to what you really want, the real integer line. So one is the real integer, the other one is what you get by approximating with this function. And you can tell, they very, very close all the way. No matter what your value is, that's a good approximation. Now, it's much better in logarithm than it is. Again, the approximation is not for the integer quantity, it's for the logarithm. So even though the logarithms are very close, the integers are not that close. It has been shown that is around 70% accurate, as in if the number is 100, you get the value from 70 to 130 roughly. A good approximation, but not exact. That's why they do the second step, which is take the guess from the first step, this approximation right here. And the second step, I'm going to show you a different picture. There's some math of it, but I want to show you this other picture that I think is going to make more sense. In general, Newton's method does exactly this. You have a guess, you want to find the root of a function that is equal 0, it finds you a better guess. So here's visually how it works, not with derivatives. Do I have a guess? Here's a guess, right? I'm taking the derivatives at that point. Derivative is what, by the way, visually?
Slope.
The what? Tangent, right? How many people know the derivative is roughly the tangent to the plot, right? So here's the tangent. And whenever that tangent intersects the x-axis, that's a better guess than the first one. So if I run Newton's method like in here for one iteration, instead of that guess, now I have the other guess. Now that's not y, I'm calling here y. That's x, the argument in there. Is that a better guess? Again, what am I looking for in here? The root. Where is the root visually? Say louder.
Where it cuts the x-axis.
So I'm looking for that value where the blue function cuts the x-axis. Is this a better approximation of the root than the first one? It is, right? And now I do what? I can repeat the Newton's method because I have a better guess. So I take now this derivative, right? And I have a new guess of the root. Is that better? Maybe it's the same because it's on the other side, but equally far away from the actual value, which is where the blue line cuts the x-axis. How about I keep doing this I take now this derivative, and I get there. Is that a better approximation of the root? Much better. How about I take this derivative, and I get there? Newton's methods is an amazing, powerful tool. That's because it's pure math, of course. But all machine learning, optimizations, convex approximations, data mining, all of that requires numerical optimization. Now, Newton's method is quite basic from 400 years ago. Isaac Newton, the guy with gravity, he figured this out. You can imagine by now we have much more powerful optimization methods that people use in neural networks, for example. Nevertheless, you can see how relatively easy, because these differentials can be computed in advance. The functions are fixed, so differentials are fixed. The actual equation to move from a null guess to a new guess, it's only this. This is a very simple operation. 3/2 times something minus something. That's extremely fast for even a slow CPU to do. So this is also very fast. This equation here, half the integer plus a constant, no problem. The PDF I put online explains how to compute this constant, if you care. And then running this, that's what made Quake 3 Arena such a faster game. Like I said, now we know how to division faster. It's not usable anymore.
How do you know when to stop finding a better guess?
When f of that is 0. Because checking, if somebody gives you a root or a guess of a root, checking if it's the root, it's easy. Usually, I mentioned this I think in last class, verifying a solution in all kinds of problems is an easy task. Finding the solution is a hard task. But if somebody gives you a guess, it's easy to check that y, 1 over y squared minus x is 0. Finding y is the difficult part. Okay? So the last thing here is to say, my student also run a bunch of code. Let me see if this works here. I'm going to make it yeah, it does work. So this is a little test with the CPU on my computer, which is a modern CPU. It's not from 1999. It's from like 2016. And with this CPU, what it says here is that that number 10,000 is running 10,000 times for different values. So it's 10,000, run the algorithm 10,000 times. If you do the normal function, just called numpy in Python, the built-in function, it takes 0.003 seconds. But if you run this algorithm, implement it in 2 different ways, I have this code online, you can download the code and play with it, but Python is not the most efficient language. You could argue that in C or Java this would be different, and it's true. See, these square root struct and square root C types are 2 implementations of this algorithm, and they are much slower. They take more time. The reason for that is, as opposed to 1999, my modern CPU from last year does the division and it's optimized fast enough. In fact, the function numpy might be built in C. So that's why it's still faster. So for today's standards, we don't want to use this algorithm because the natural way to do division, it just does it fast enough. But in 1999 was a big deal.
Possibly putting like a lower level language that this algorithm
Yes, that's what I said. Python is not a good measurement language because it's a high level language. Very good for development, extremely useful in practice. If I were you, the first language I would learn is Python. If I would know only one language, that would be Python. But to optimize things at scale, as in, Google search engines or machine learning, you can't really do it in Python. You have to do it in Java or C. Okay? So this code, the PDF, and all those pictures are online. I'm happy to talk more about it at office hours if you care. See? We can. So now we're going down to earth. Okay, we're back to the CS 1800, and we have to do logic gates. That's what the other sections did for like 3 lectures. We're gonna do it in 40 minutes. I'm counting on the fact that you guys have seen some of this stuff, and if you haven't, it's quite easy to catch up. Okay? Not all extra stuff will be at that level, okay? That's a little bit exaggeration. So now we are at logic gates and circuits. So we're moving away from binary, although not completely away. Let's do a little binary addition here, which is by bits. So here's bit A, here's bit B, and here is the result, which is the result bit. We can call it, I guess, sum. And also we may have a carry. In the result sometimes we can say this is C. So right, when we add two things, two bits, we get the value that we put down, but we might have a carry bit for the next round, right? So what are the possibilities? 0, 0, 0, 1, 1, 0, and 1, 1, right? And if I add 0 to 0, what's the sum? 0, what's the carry?
0.
0. 0, 1, what's the sum?
1.
1 carry?
0.
0. Sum is 1, carry 0. Sum is
1. Or 0. 1.
carry 1. You can tell we went back to earth, right? 0 plus 1 equal 1, right? And not the same as Newton's method. Okay? So people have wondered, how would that look in terms of logic if 0 corresponds to false? That's the logic. 0 is false and 1 is true. Or in people who are engineers, 0 means current doesn't pass through. 1 means a line that current passes through. Right. Sounds about right. So that's what we're going to do next. What are the logical equivalents of this stuff? We can, this is the addition, that what we've done already. So we kind of map into analogy in like kind of the same thing. It's not addition, now we call it truth table. Because now we think of not as bits, but as true and false variables. 1 is true. Sometimes people call it Y from yes, and false, no. Please don't use yes and no. Please use true or false, or 0 and 1. But if you see yes, that means 1, and no means 0. So how do we do n? It has a point, n. Same thing, A, B. Actually, let's build a bigger table so we don't waste our time. A, again, 0, 0, 0, 0, 0, 1, 1, 0, and 1, 1. Those are the options. And if I am to end them, I'm going to go fast because I'm assuming that's easy to follow. If it's not, no big deal. Come at office hours, tutoring, recitation, and we'll work a lot more on these things. What's 0 and 0? 0. 0 and 1? 0. The notion of and in logical terms, and means they have to be both true, right? I've got a girlfriend and a house. And I have to have both, right? To work out. Right? 0, and this only the girlfriend and the house is here, right? Good. How about or? For or in logical truth, only one has to be true, right? I have a girlfriend or a house. I don't have enough money, so I can only afford one. So 0, 0 means I'm really poor, right? Means I get nothing. 1, 0? 1. 1. 1. Just like with binary, I would strongly encourage you to go by what makes the most sense to you. Different books will talk in different ways about those things. Different instructors will talk in a different way. Different TAs talk in a different way. you should take the advice of think right in the way that you understand it. Because there's many ways to think about this, they're all equivalent. Whatever way makes the most sense to you, that's the way you should use. So also, we're going to add something to it. We're going to add a little circuit, which means the same thing. So here's an end circuit. I'm going to try to write it here at the end column. Here's how it goes. Here's the current. There is a switch. It's called this switch A. And it's the current, so the current goes this way. And there's another switch here, switch B. Right? And that's the result here. And the meaning of this is, how do I get the current to pass through? At the source, if this is the source, there's current in the source. It's like the plug on the wall. How do I get the current to go all the way here? I need both switches to be pushed down or turned on, right? Imagine a lamp that has two switches on the cable from the wall. Unless you turn both switches on, the light won't come out, right? So this in here says, for the current to pass through, you need both switches to be on, otherwise the current doesn't pass through. And there is a conceptual representation of this, which is saying, so that's the circuit, and here's the gate, saying you have A and you have B, and there is a sign that means AND, which is kind of I think it's a little sharp. I never got the drawing right. It's kind of round, like that. This means an AND gate. And people sometimes put a dot in here. That's an AND gate. So this is a conceptual drawing. That is not the way it's implemented. It's not how circuits work. It's just a logical drawing. When you see this, it means AND. This is the circuit. That's how you would build it on a silicon. You have a wire, and only if both two switches push, the current pass through. And that's a truth table that tells you the value that you should get. How about OR? How the circuit looks for OR. So now I'm going OR. Here is power. Power now distributes into the two switches. This is the A switch, and this is the B switch, right? And then it comes out. When do I get power here? This is important to understand about those circuits. If you haven't seen those kind of drawings, you gotta see where the line connects. What do I need to push? One of them, right? If I push either one of them or both, I get power. And there is a symbol for this, which is A, B, same bar here, and this is kind of a little, it starts like the other one, round at the top, but then it goes like this. It's like a bracket type of thing. And sometimes people put the plus sign on it. This is not necessary. So the idea of this dot and the plus have to do the analogy with algebra. Plus is kind of like the addition, because OR it's analogous to addition, and this is analogous to multiplication. People have looked at this table and said, it's not quite right, but the analogy is, when do I get AND in 1? It's kind of like multiplication, when both of them are 1. And when do I get 1 in the OR? It's kind of like the addition. If one of them is 1, at least 1, I get 1. Of course, that's not really true. 1 plus 1 is not 1. But the analogy, that's what explains this plus sign and the dot sign here in the case. That's not mandatory, but people who have a hard time drawing this, like me, may look like that. So then if you put a plus, makes it more clear which one is it. But if you draw it nicely with those curly brackets, you don't need a plus.
So is that how exclusive OR works? It just adds it together?
I'm getting there
Okay.
in a second. Next one, up.
Does the 4K look more like the Star Trek sign?
It's like an arrow.
Maybe I have a hard time drawing this. So it's kind of, I think we learn it as a curly bracket. You should look online for an artistic drawing of it. You know, that's what I've got here. So you may be right. It's longer like a spaceship kind of thing. Okay, who's with me so far? Easy, right? Good. So now we've done that. Before we do sort, like somebody asked for, how about not? Not, it's really easy. Let's. I'm gonna reserve that there, but I'm gonna write on the left side. So how about not? Say not A. When A is 0, not A is, not means reverse or negate. So when A is 0, not A is 1. When A is, again, 0, that's 1. 1 is 0, and 1 is 0. So I could do the same for B. Not B will be, when B is 0, not B is 1. When it's 1, 0. When it's 0, again it's 1. When it's 1, it's 0. So how does the circuit looks for not? I have a wall socket, and we draw it this way. That's the circuit here. That's the A switch. So the meaning of this is when A is on, pushed, the circuit is disconnected. Right? It's the different drawing than in here. In here, when A pushed, it's like a button. Think of this A as a button that you can push on. When you push on, you connect the circuit. In here, when you push on, you disconnect the circuit. Right? So when A is on, you have no power. When A is off, the circuit is released, the push button is released, then you do have power. This is just a conceptual drawing, and for me, it's easier to think in this way, like a truth table, but for engineers, it might be easier to think of silicon and buttons on the wire. In this case, this is a button that when you push, closes the circuit. This is a button when you push, disconnects the circuit. And we have a gate, of course. The gate is, here's A, and it goes into this triangle with a little circle. So what comes out is not A, and that's a sign, by the way. Not A, it's written in logic as this gamma sign or square sign, not A. When you see that sign, that means not. So I should say for all gates, what comes out of them, this is A and B. How do we write AND in logical terms? There's a symbol for AND, right? Everybody knows that? It's not round. What's the symbol? It's a V, right? Backwards V. A and B. So AND is like A and B. And OR is, what's the symbol for OR? Like a V right there, right? B. I mean, you have to know those symbols, but they're just another alphabet for writing the stuff that you already know. Instead of writing OR and AND in letters, you can use that symbol, and you get Boolean algebra. So we should write here that this is A or B. That's what comes out of this gate. And here's not A. Okay. We're doing okay. How many people have seen this stuff before? Almost everybody. That's what I was thinking, you know. Doesn't make sense to spend 3 lectures on it because you've probably seen it. And if you didn't, you can just, you know, one afternoon and you are catching up. So how about we do a little example here? I'm going to do 3 things. One is like a particular table. So particular table. You can think of this as what I want. So we want the following circuit board, AB 0, 0, 0, 1, 1, 0, 1, 1. Suppose we want this to be 1, 1, 0, 1. We want to know how to achieve that result. How do we create a board that does that? And that can be achieved conceptually by the following formula. So this is called a Dnf formula. We're going to explain in a second what DFS means. I'm going to write it down and you guys can explain it to me. Explain to me, how did I come up with it? How many people can see that this formula achieves this result? We're going to pause for a second to give everyone a chance to say, why is this formula achieving that? Looks like a complicated formula, but the construction of it is quite easy from the table. We give everyone 20 seconds to see, do I see why this table corresponds to this formula? While it looks long again, it's actually quite easy, the correspondence between the formula and the table. So now, I'm going to ask some questions. Why do I get 3 parentheses? Yes?
Because there's 3 values returned true.
There's 3 ones. And between them, I have what? Or. Whenever I have parentheses with or between them, that's called DNF. So whenever you see parentheses with stuff in them, it's not really anything. So there's some constraint about what you can put inside. The idea of these parentheses with or between them, that's a DNF formula. It has a name, junction normal form. Nobody can remember their names, just remember it's DNF. Okay? So that's a DNF formula because it has those parentheses with ors between and ends inside. That should be also specified that I have ends inside. Now, where do I get these ends? How do I look at this and say that has to be one of the parentheses? Why? This is what in here? Not A, right? Not A and not B. When I have operations like that, who gets to be executed first? Is the not executed first or the end? I mean, there's a, or like in additions and multiplication, there is an order of what operations happens first. Which ones happens first? The not. So not happens first, not B's first, then not A, then the ends. Between ends and ors, I have to put parentheses to indicate which ones happens first. Because I put those parentheses, the ends will happen first, like with normal algebra, and then what's outside parentheses will happen later. Yes?
You see that all DNF formulas with ands inside the term?
Yes. There's a formal definition. You have to read it from the book. But the trick for you is not to know the formal definition. In this class, the important stuff is to recognize that some formula is DNF. And there's another one which is CNF. If you remember that between parentheses you need or signs, those are the DNF ones. But yes, you have to have ends inside. Okay, so this corresponds to what? Where is not A coming from? Why is not A here? Yes?
Because on the way left it's 0 and A.
Exactly. So these parentheses corresponds to this row, right? And this 0 here corresponds to not A. How about this not B? That's the 0 of B. How about this B in here?
The 1.
Why is this B and not like before not B? Because these parentheses correspond to the second row, right? So there's a 1 here, that's why I get a B. And these parentheses corresponds to this row. Now, those are equivalent things. This DNF formula is equivalent to this particular table. It does the same. What does the same mean? When I say a formula and a table do the same, what do I actually mean?
When you get plugging the input so that it's the output.
Right, it gets 1 whenever the table gets 1. So in this formula, if I plug in those values, I get exactly these answers. That's what it means to be equivalent logically. Okay? But I can also build a circuit with gates that will do the same. Yes?
Why can't the last parentheses be connected to the third row?
This row?
Yeah.
Well, it's A and B has to give me 1.
Oh, it only gives the 1 values?
Right, so each parenthesis, the way I build this formula, which is not the only way, but the way I build this formula, is to say, I'm going to look at the ones.
Okay.
And I say, when do I get the 1? I get the 1 here, or here, or here.
Okay.
And this corresponds to the 1 lines.
Okay.
So I read each line, for example, this line, I say, what does this line mean? If A and B are both 1, so I write A and B, I should get the 1.
Okay. Thank you.
And this is quite a constructive way to construct any formula from the table. It doesn't mean it's an efficient formula. There's probably a much shorter formula which does the same. So we can do Boolean algebra and manipulate this formula, just like you do arithmetics and manipulate numbers, and you get a much shorter formula. We'll do that in a second. But before we do, I want to build a circuit that achieves the same result. That is a bunch of these drawings. So how do I do that? Here's how I'm thinking about it. I'm going to draw from the beginning A and not A. So I want a line that says this is A, this is the power line corresponding to A. And to get not A, what do I have to do to get not A? So if this is A, this is going to be not A. See, I put this not gate here. That means if this corresponds to the power line, electric power of A line, then this line here will have power exactly when this one doesn't, and the other way, right? So I put a little not gate. Now I get both signals, A and not A. I do the same for B. So here's B, and I put a gate to get not B. So here's not B, and this is B. Now I get all the possible inputs, right? I've constructed all 0, 0, 1, 0, 0, 1, and so combinations because I have all 4 lines. A, not A, B, not B. So now I have to build these gates, right? So what is this gate? This is an AND gate. But it's connected to what wires? Not A. So I make a connection. I put a dot that means connection. Wires are like glued with like soldered in. You ever see one of these green silicone boards? How it has like soldered in stuff? That's my notation for solder. So I connect this wire with what wire? Not B, right? And what gate I need here? Which one is it? This one here, right? So this is the nice round one. See, I think it's a little bit more. I never got these gates right. Maybe you guys are more talented at drawing. So what comes out here is I can write it down just to keep track of things. Not A and not B, right? That's what comes out. How about the next gate? Not A and B. What is that? I took the not A lines and I take the B line and I construct the gate which is not A and B. How about the last gate, A and B? What lines do I need? I need the A line and the B line. Who's with me? Come on, who's with me? You guys gotta get this stuff. It's super easy. I mean, unless you have some sort of drawing misunderstanding, like confused between round and sharp and stuff like that, this should be like 6th grade kind of stuff. And then, how do I deal with these ORs? I could deal with 2 of them at a time, so I need a bunch of OR gates. But for simplicity, what people do, here's my 3 lines coming. I can put a big OR gate through all 3. So this is a triple OR gate. It works the same with N. So I let it you guys to think about it. I could have done it without doing this. I could do an OR here, right? Or those 2, get a line, and then OR this one with the result. So I needed 2 OR gates that way. But instead of doing that, I did it with 1 OR gate that ORs 3 lines instead of 2. Right? So that's my circuit for this formula. Now we have 3 things. The table, the formula, and the circuit, they do the same thing. Whatever input is given here, this line, the final output, right, this is output, will be the same as the formula output, will be the same as the table output. So, let's see how we're doing with time. We're not doing bad. So I kind of tend to think, I think the book presents things a little differently as an order. For me, I got educated in a math department, not in a computer science department. So I went to a math school, and in fact, in my country, when you go to math school, you do only math for 4 years, nothing else. Math, 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 math until you drop dead, okay? So the way I learned those things, we learned it at the same time. We didn't learn it first, the truth tables with signs and ORs and all that, and then the formulas, and then the circuits. We learned it at the same time. For every table, we have a formula and the circuit. And for every circuit, we have a formula and the table. So that's why I think of them in sync. Every time somebody says, I have this formula, in my mind, you have a table and a circuit, because they all mean the same.
Do we have to draw the closed circuit for not this other type?
Which one?
The push buttons. There were like 2 types of circuits.
Right. If I want to do the push button, I should say this is the power line, right? And then A, it's a push button, right? But we don't draw that. We just write directly A is this line. But I could have said there's a power, and this power outlet distributes to A and B, but then A is the push button. So I could have done that, but for simplicity, we don't draw the power source, we just draw the A line, then we get the non-A line. Okay? So I think of those 3 things in sync all the time. But if it's easier for you, if you prefer the truth tables, maybe you want to manipulate truth tables and then only at the end derive a circuit or a formula. Some people prefer the formulas. I've seen a lot of people who are much more comfortable with the formulas than with truth tables and circuits. So then you go by the formulas and you see what you get. So there's a bunch of rules here. And we kind of want to do an analogy with real algebra, let's say normal algebra. So here's a rule that says A or B is the same as B or A. It's true, right? Or is a commutative operation. What would be the analogy on this side? Let's say x plus y, to not be confused. Let's say those are Boolean variables and those are numbers. Numbers. X plus y is the same as y plus x. Now, this analogy doesn't mean anything. It doesn't mean that this algebra has to work like that algebra. It's just maybe a formal mechanical way to make analogies. And works the same way, right? That would be x times y is y times x. How about A and B or C, what do you think this is? Kind of open up parentheses. How do I do that? How about x times y plus z? What is this? In normal algebra. X times y plus x times z, right? Are we familiar with this?
Yeah.
Yes. We have to be, right? So what's up in here?
A and B or
A and B or A and C. Now some people believe there is a precedence. Like if I write it that way, everybody should know and happens first and all. I honestly, I don't know. So if I don't know, what do I do? I put parentheses to make sure. Because this is conventional. Even if you read somewhere formally, this is how it is. Maybe the guy who reads your paper doesn't know that. So just put parentheses when you're not sure, okay? How about the other way? A or B and C versus X. Well, let's see if there's an analogy here. I'm not sure there is. What is this? A or B and A or C, right? Is there an analogy in here? Hmm?
It would be something like x plus b y times c. So there's no real analogy.
Right, so I don't have time to do this in class, but if you want to go into formal algebra and topology, if you care about such things, that's a good starting point question. Since this works as a truth table, and it does, right? Everybody believes me that if I plug ABC, how many options for ABC are here if I build a truth table? How many rows that table would have? 8, because there's 2 possible options for A, 2 possible options for B, 2 possible options for C. So to check that table, if I'm not going to do that, but to check that table, how would I do it? I want to verify this formula. So here's what I'm going to do. I'm going to write A, B, and C. The options being what? 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Did I skip something? I did.
No, there's 8.
There's 8? Okay. So I have to compute, to verify this formula, on one side, I'll have to compute A or B and C. That's the left side. And on the other side, I have to compute the right side. A or B and A or C. I'm not going to do all rows, but I'll do 1, 0, 1, 0. How does this row works? 0, 1, 0, if I plug it here, I get what? 0 or 1 and 0. 1 and 0 is?
0.
0 or 0, I get? 0. How about in here? 0 or 1,
1,
1, and 0 or 0,
0,
0. And then 1 and 0,
0.
0. So to verify that formula works, it has to work for all lines, not just for few lines. For that formula to be true, it has to be true all 8 cases. Because that's what it means to be true. Now again, I leave this as an exercise. Is there an analogy or not? What else? Anything and truth. Truth means 1. Right? Is what? Anything and truth. A. Is there an analogy here?
8.
X times 1 is? How about anything times 4 and false? Is what? False. The analogy being?
X times 0.
X times 0 is 0. Right? How about a or true. Or true. That is what?
True.
Always true. The analogy being?
X plus 0. Like just 1, I don't know. No, it's hard to get.
X to the 0 plus.
Oh,
X
yeah.
plus 1 is 1. Again, question marks all the way, because
Yeah.
this is kind of an exercise for you guys to figure out what the analogy. And the last one here, X or false is, A or false is? A, the analogy being X plus 0 is
X.
So this one and this one didn't quite work. That's why this analogy is more like, okay, a guideline than reality. So you can take this as a topology exercise if you care and figure out what is analogy. And if you want to go further, assuming there's no analogy, why there's no analogy? There's something missing in normal algebra to make an analogy out of it. There's some principle that works here, but not there. That's how topology goes. And we have two more that are the negation rules. So negations, which says if you negate A and B, what do you get? How negation distributes to an end? Yes.
Not A.
Not A.
Or not A.
You guessing? Or you know the answer?
I said it wrong.
Guessing is fine, right? I mean, if you guess right, who's gonna know? Problem with guessing is that eventually you're gonna guess wrong. We have one more negation rule, which is if you negate A or B, what do you get?
Not a B and
Not A and not B. Sometimes those are called, they have a name, De Morgan. Not all countries know what De Morgan means. In the United States, people give names to everything, but if you go to other countries, they have no clue what De Morgan means, okay? They just know them as negation rules. Now, those rules are very important because those rules are used to make proofs. They are essential in logic arguments, like type of contradiction arguments. And for those rules, this you can kind of see mechanically and apply them mechanically, but when you make a proof, you have to really not just understand, but be extremely fluent in what this actually means. The negation of having a girlfriend or owning a house is what? Not having a girlfriend and not owning a house. That's going to come up really quick, as in next week, in terms of how do you build a proof rigorously. Where you may have an intuition of something that looks like right and appears to be right, especially with numbers that are quantities, it seems like the number is okay. To make a formal proof, you need arguments that are based on those laws. Contradiction, let's assume that something happens, but we also know something doesn't happen. The contradiction implies that we are assuming whatever the negation means. So those rules I have to insist. They are not more complicated than this. The trouble with them is that while for those you can apply them mechanically and read the results, not worry about it, just apply mechanically the rule and get whatever comes out of it. For those, you're gonna have a very deep understanding of what is actually A, not A, B, and not B. And in your proof, A may be, I'm assuming there is a prime number bigger than 1,000,000. What's the negation of that? I'm assuming something. And then building proofs, we have to breathe these laws. Not just mechanically, but we have to really understand what they do. So there's a lot of notes posted online with example, assuming A, I've been to the market. Assuming B, I couldn't find milk. What does that mean if I negate it? So you really want to think of this in terms of statements that are various statements, not just as Boolean variables. So now let's apply these rules to this formula here and see what we get. So I'm going to say not A and not B. I'm going to leave that parenthesis alone. But then I'm going to distribute this in here. So I want to make a bigger parenthesis out of this. And I say this is not A or A and B. So this is that. I didn't change the first parenthesis. Or is this or sign? Now, how did I get B and A or not A to be this? I apply the distribution or and against the parenthesis, right? If you think of this B as a common factor to this or parenthesis, it's B and A gives me this, and B and not A gives me this, and the and, the or sign is the sign in here. Which rule is that? It's this rule right here. Except the common factor was on the other side. How many people see that this rule is the rule that's being applied here, from here to here, right? Now, I'm going to say this is not A and not B. Same, I don't change this. I'm going to call this truth. I'm going to say A or not A, it's always true. Agree? One of them has to be 1, the other one has to be 0. The or sign between them makes it always true. So then who is true and B? That's B. So now I have B or a parenthesis. So what do? Not A or B, right? Then what? And this end is this end, right? And then what's the other parenthesis? Not B or B, right? I open this B against an end parenthesis, and I apply then, the or sign was here, I applied this rule. This is the one that distributes an or across the ends. So now what is not B or B?
True.
True. So then true and something. What is true and something? 3 and something. 3 and an orange is the orange. Right? So then I'm just left with the orange, which is not A or B. So this is how Boolean algebra manipulations work. You apply those rules. You can apply them in any order you want or however you see fit, as long as they're correct. And the purpose, of course, like in algebra, like in normal algebra, is to get something more simplified. So I could add to my verification table here that this formula, what was it? I guess it's not this table, sorry. I could say this circuit is equivalent to this formula, which is equivalent to that truth table, the circuit, and this formula does the same as this formula. If I want to verify them, I can plug in ABC values and get the same answer.
Can you just explain how you got the second one to again?
This to this?
No, one more.
This to this?
Yes, please.
True and B?
Yes.
B. Right?
Yeah.
And then I distribute this B or against the parenthesis. I'm using this rule. So B or not A, it's here. Maybe make it more clear. B or not A, if I do this like that, more clear. B or not A. And then B and not B. So when I distribute this B, effectively what I'm saying there is B times or. Not A and not B is B or not A and B or not B. Maybe that's easier to see. Now this is the same as that, it's just written backwards. Not A or B, and this is not B or B. Any questions about this? Now, this, it's easy when somebody shows it to you, you know, like, okay, did you guys follow? Seems easy. It's actually a little bit harder to do it by yourself, so you need practice. There's no way around that. So the next week we're gonna hit you with like 100 Boolean formulas that you have to manipulate. But there's no magic to it. It's not like, okay, highly intellectual stuff. Just you need the practice to not get stuff wrong. That's all. So next up, we have 2 more gates to do here. So do we still have that board with the, we don't. Here are the 2 gates that we're gonna need, N, A, and D, which is not N. So how does this look like? Here's A, here's B, 0, 0, 0, 1, 1, 0, 1, 1. That's my truth table. So if I'm to negate N, what do I get? 0, 0, and is 0, not and is 1. 0, 1, and is 0, but not end is 1. 1, 0, the end of them will be 0, so the not end will be 1, right? And 1, 1, the end of it is 0. I should 1, sorry, and this is 0. I was thinking. So this is not end. Let's put the end here just for you guys to have a reference. This is the end column. That's not end column. Okay? If you watch this video again, or if you write the notes again, it should be clear that's not end. The other one we need is XOR, which is called exclusive OR, and means exactly 1. To be 1. So there's a difference between XOR and OR, which OR means either one to be 1. So in OR, I have 0, 1, 1, 1, right? The only time I get 0 is 0, 0. In exclusive OR, I need exactly one of them to be 1. So in this case, 0, 1, that's good. 1, 0, it's good. 0, 0, there's now ones. How about 1, 1?
Oh, no.
0.
0 because it's not 1, it's both. Okay? Now, we're gonna continue from here, and the NAND gate, I wanna just say the last thing today. NAND gate is particularly critical because it could be implemented very fast in silicon, and because all the other gates can be written with NAND gates. So NAND, in terms of engineering hardware, much more important than the other gates. Because if I build NAND gates efficiently, and I can, then everything else is just a band of NAND gates. So here's an exercise for you. How would you write an AND gate, or an OR gate, or a XOR gate, purely made out of NAND gates? So take a XOR gate, for example, and try to make that XOR gate based not on the inputs passed through NAND gates. One more thing, as part of the extra, I don't want to connect my laptop again. I show you the Radix sort. There is an exercise, an extra exercise. It's called 2 cards that asks you to do effectively Radix sort in binary. You can download that PDF, cut it from a piece of paper. There's some cards there, like library cards. You cut those carefully with a scissors, and then the exercise tells you how to do Radix sorts in binary with those cards. That's all extra. Have a good weekend. There's an online homework due and a class next Tuesday. Oh, one more thing, very, very important. I'm not sure when the recitation quiz is going to be. I know the website says next week, but I'm not sure that's true. By Sunday night, we'll know for sure if it's next week or the week after. Yeah. You have to know the symbols. Yeah. sure that's true. I mean, if the problem says show your work, it's a little thing. I understand what you're saying. You know,
Yeah, that's what I got. What is it? Is this your first class? Yeah, it's my first one.
because even if you don't do some exercises right now, what about 5 years from now? Who knows what you're going to do? And you're going to logic report, they write it away, and you say, okay, everybody's going to class.
Well, your syllabus are
This guy. So I think it's for the homework it might be okay. I'm not sure. I would say you're okay, particularly here. But for your own experience, I think you should come up. They're going to come up.
Yeah, like I need to leave it. I've done that much.
Wires and gates and all that.
For exclusive for, if you have multiple cores,
Yeah. So exclusive or of 3 lines. 1. That's what I think. We should verify that.
Yeah.
I don't want to give you the wrong answer.
exclusive for is my favorite operator.
Exclusive board has a lot to do with learnability.
Yeah.
And predictions and stuff like that. Yeah, I do.
10 seconds. I hope it works.
Hi. I am on the cross-country team, so I need to give you one of these. This is just a travel guide.
What
For your competitions and stuff.
what does it actually mean? I don't care much about this, but I care about what it means for you.
Yeah.